Hi, my name is Dennis. Welcome to Foundations Networking, Proxies, and Payload Inspection. Let's go ahead and get started. Our learning objectives today include learning what proxies are and what are the use cases for proxies. No, not proxy voting for any kind of investments, but proxies in terms of software. We also want to identify the varying devices that could act as different proxies. So there are such things as different proxy types that we'll learn about in the upcoming slides. And we utilize tools to dissect and analyze traffic utilizing proxy technology, including the idea of protocol termination for any kind of encrypted type traffic. Let's move ahead. So we'll go over proxy overviews and figure out what exactly does it mean from a proxy in a network perspective, and what kind of use cases and applications we need to look at when determining if we need to use a proxy or not. So proxies are for different things: caching, as mentioned earlier, protocol termination, which means decryption, and sometimes IP masking. We have a human analogy right here where we have Bob and Alice talking to each other. But instead of Bob directly speaking to Alice, you have a proxy in the middle, creating a translation in between, and so that Bob may never have actually speak to Alice directly. This goes directly with what we called IP masking, which if Bob had a public IP address of 1122.3344, and we had the idea of Alice communicating with Bob, maybe we don't want them to know my actual public IP. And so in this case, it might be 88889999 instead. And so Alice actually makes a connection to 88889999 instead of 1122.3344. And likewise, the verse, Bob actually connects to the same proxy to speak with Alice, and that connection is made on your behalf. And they're common for modern networks for interception, as well as web content filtration. And there's the idea that Bob is going outbound as opposed to coming inbound. When we look at proxies, we also need to think that proxies always operate at a higher level, right? Proxies always operate at layer 7. And so what are other protocols that operate on layer 7? Well, we have things like HTTP headers. Remember that HTTP headers are stateless, but also, again, proxies, HTTP, DNS, right? These are all stateless based on protocols, but they're all at layer 7. So only applications understand, so proxies are being an application, understand what happens. Lower level protocols have nothing to do with this. At this point, the applications need to understand if we're having what's called client server resolution issues and other things of that nature. So you really have to understand at this point what the payload means as opposed to focusing on the handshake itself. In this case, we have HTTP, which is a stateless protocol. It has the idea of a client request as well as a response from the server. So there's all this. There's a client. There's a server. The client wants to post something to a particular web page and it provides header information accordingly with their key value information. And it might have a good chunk of data. We have a start line, the headers themselves, and an empty line that must be put in as part of the HTTP specification, as well as the body for any kind of return information. The response will say, hey, you're not allowed to, you're forbidden. Here's anything extra I want to put in, and here's the header information coming from me. In addition to HTTP headers, you also have HTTP methods for hypertext transport protocol methods. So concepts include the most popular, like GET, which is get data. So when you surf CNN.com, for instance, and you're actually getting the main page, this is what it looks like inside, and we'll capture that in the logic when we create our own local proxy. We can also put and replace data. Put and post are similar, where that put is actually replacing and updating data. Post is merely updating net new data. Right? New data. And based on APIs and the flexibility of HTTP, you can actually create functions, which we call application programming interfaces, or whole applications themselves, or websites that you can say specify a URL and an HTTP method together, and it does this one thing and one thing alone. It's supposed to use surfing a website, clicking on something. You can have direct access to an application logic and make things happen, such as create, replace, or update and delete. HTTP methods can allow you to have those CRUD operations. Again, CRUD is based on creation, replacement, updates, and deletes of data. You also have HTTP header parts. Now, in tandem with your method, here's your method, here's your response with a response code. You also have things like header and key value, which we have a cookie value here. We also have parameters. Each parameter is started with a question mark and an equal sign, and then segmented with an ampersand sign with another equal sign with a key and a value pair here. In our case, we have our first parameter for posting a login, which was post the data that I want to log in as u equals, which is likely user, foo, which is my value pair, and then another key, which is p for password, equals the value of bar. So we have user foo, password bar, posting that information to the web application. Once I get all the proper authentication and assuming that the login credentials make sense, I'll get a cookie for my session back, which is generated by the web server. And that is the value of s equals, right? Session equals 01A, etc. Now, this is just a simple method. And notice that we're not using security, which is HTTPS, SSL encryption. Now, HTTP headers are wrapped inside all of this. So if you wrap everything in a nice SSL package, you might see your little padlock right here inside your browser. So your browser will do HTTP methods and requests on your behalf. And while that's not a proxy, that's just the client doing so with different things like parameters and values to help the application understand what we're trying to do. Now we saw HTTP status codes of 200 OK, which means OK. The process went through greatly. We also have other HTTP status codes. So you'll likely see 200 OKs in most successes. You might see 301s and 302s for redirection from a URL to another URL. So 301s typically happen when you say google.com and might redirect you to www.google.com instead, right? And so it would actually redirect you. Your client would go out and do a DNS query for a CNAME for www.google.com and then get back the IP address accordingly. Another common one is client error. So anything with 4XX or 401, 404, you're either unauthorized, forbidden, or a file not found. You requested a wrong or file that does not exist. 500s are typically an API or server-side error, which means there could be a capacity limit or an application logical error based on your original query. However, regardless of your HTTP status codes, you should look out for anomalies whenever possible. High counts of 400s and 500s could denote a problem with your application. We also looked at the concepts of SSL and TLS termination. SSL being secure sockets layer, TLS being the transport layer security, which is really the successor to that. Both mean the same thing from your perspective of encryption. The main thing is SSL and TLS termination now encrypts something that wasn't already provided. So let's say you had a web server that has a legacy HTTP service that has no native encryption. You will use a reverse proxy that acts as a load balancer to terminate the connection. So inbound would be secure, and then internally here would still be unsecure or secure if you desired. And it'll go ahead and allow security over the internet as opposed to security over the private network, thereby giving you potential compliance and increased security needs based on SSL. And just like with TCP, SSL and TLS are stateful, which we have a handshake right here, and it monitors the actual encryption. So you create a session tunnel above, and you exchange your keys accordingly, and it's handshake. And then finally, it moves from a public key secret exchange, which is usually Deathly Helmet nowadays, noted by DH. And then a symmetric session key is created for the remaining encryption for faster speeds. So we talked about proxies and what they are. The forward direction always means the client goes outbound to the internet. Those are called forward proxies. We're going forward to the internet. And they're great for content filtration, caching, and rarely IP masking nowadays because we have network address translation with source padding. You really don't need that for masking an IP unless you're trying to use a virtual private network, perhaps other proxies on your behalf through your internet service provider. The main thing about forward proxies and one of the main use cases is to filter web content traffic. If you wanted to block or allow google.com versus bing.com, you could do that using a large enough proxy server. Also, things cached in memory, depending on the proxy server settings, you can allow anything that's commonly downloaded to be cached directly to your network as opposed to the clients reaching out for it each and every time for something like static images and main text files. Okay, so for proxies, we actually need to correct that. That is reverse. These are reverse proxies. So outbound coming inbound is actually what you're looking at in outbound. So reverse proxies are essentially load balancers. Load balancers are exactly what it sounds like. It balances loads coming inbound to any kind of backend. So you might have multiple web servers for the sake of scalability, handling multiple traffic clients. All right, remember, reverse proxies accept coming in from the internet, not going out. Now, in addition to the direction, proxies also can be explicit or transparent. Explicit ones require you to say, I need this IP address, and here's my listening port. Funnel all web traffic to this, but we have to make sure that when using explicit proxies, my application is proxy aware. If it isn't, it cannot go to the proxy. Some common protocols for it include HTTP proxies, HTTPS proxies, SOCKS, and many others. You might see these as options inside your browser or your application that supports proxy aware support. What if your proxy does not have support? Well, I mean, what if your application does not have support for proxies? Well, you use what's called a transparent proxy, and this is usually at the network level. You can utilize any ports, really 1 through 65,535, and then you can actually have no proxy awareness whatsoever. The client and the server transparently do not see the proxy itself, and it only understands that traffic can either make it or not. Proxy can make decisions, and you can do so on multiple ports as opposed to just one port. Now, there's a lot more resourcing information and issues with that, such as your UTM, your Unified Threat Management appliance, such as a firewall with layer 7 awareness, could act as a transparent proxy, especially for data loss prevention rule sets. Keep in mind that these are two different concepts, but they're two different use cases and applications. Local proxies using explicit proxy requirements are usually better for short scale and one-on-one needs. And transparent proxies are better for masking scale at networks items. So anything that doesn't require proxy awareness, transparent proxies might be your best bet. Now let's move into intrusion prevention systems and understand how that plays with proxies and payloads as a whole. First and foremost, we want to have normal TCP data patterns. So what does good look like in terms of TCP? Again, you have the three-way handshake, and on top of that, remember that we have sequences. Sequence 1 starting with a length of 669 of total bytes. I acknowledge it with my own acknowledgement number of 670, which is sequence number 1 plus the length. The next one up, after I created that handshake and to keep acknowledging that I've received the data, I'm seeing sequence number 670, and it's going to be a length of 1460 this time. Now I acknowledge both of those together, which equal 2130. And the same back and forth keeps on happening until the closure, and the last bit of data goes through the pipeline of the buffer. Again, one sequence number and acknowledgement per segment, and the sequence number is based on the length. Sequence number and length is based on the byte count. So how much I send data is how much I acknowledge as receiving the data if the client, in this case, is sending data. So for instance, where would this apply? Let's erase all of this here so you can have a better view. So let's say I'm sending an HTTP post. I'm posting originally 600, 1460, 1460. Let's say I'm sending about 2,000 bytes of data or 3,000 bytes of data. It gets broken up into chunks inside data segments, and then it starts sending the data after my initial connection over TCP, doing the post and sending this via the TCP and allowing TCP to handle the segmentation of the data as well as the reliability of how that data gets sent. HTTP is just doing so until the connection finishes. So anomalous behavior for TCP include multiple syncs and ACKs together. So if you have a large amount of sync requests coming in from the same host, multiple hosts, and you have large amounts of waiting for the final ACK to happen, which may not happen to the visitor, such as large amounts of send ACK half-open connections in your state tables could cause a denial of service. This also can be reflected based on spoofing of different fields of SYN and SYN-ACK. So if I have an attacker, I'm spoofing that it came from the source IP of the victim, which is right here, and it's going to go ahead and give me SYN-ACKs, right, back to the victim and fill up their internet connection pipe, usually from servers and whatnot. That's called a basic denial of service using reflection. Now, the botnets and then all the actual scalability of this gets really large and really complicated to look at. But this, from a basic SYN-ACK flooding perspective, having too much of a good thing is usually a bad thing. So, too many half-open connections, usually with SYN-ACK as they're going outbound, and never any responses with exhaustions connected for acknowledgements. Another thing that has IP options capabilities, IP fragmentation and assembly. While we know that packets can be divvied up based on usually 1,500 bytes in length, you can actually further fragment IPs based on maximum transmission unit, transmission unit. So while this could be 1540 in most cases for Ethernet, maybe you might have networks that only support 300 bytes. You have to fragment those packets together because you can't just reformulate and resend the data. Let that be handled at the routing level at layer 3 instead of the application layer. So a 4K chunk is then divided into multiple bytes that you see here. And then, of course, those have offsets associated with each segment, as well as the end, so the total length, plus the length of that segment, and the offset from the last one. So offset 1, offset 2, offset 3, hopefully all are in synchronization and tandemness. You would never want to have overlapping segments in this case. That's all you really need to know about IP fragmentation. Now, anomalous fragmentation includes overlapping, right? Overlapping of reassembled. So if something was larger than the original length count of 2,000, once reassembled at the client TCP stack side, let's say it got reassembled at 2,500 bytes. That's an error and could cause a denial of service condition, but usually it should be dropped. There's also the idea of multiple fragment overlaps, which let's say in my offset says I'm right here versus right here where it should be. It'll have an overlap, which means data can either be overwritten or crashed depending on the stack level of denial of service. Those are considered informations that you should keep in mind when looking at and examining connection. What's considered normal HTTP? Well, we saw that there was always a request and a response for every request. There is no asynchronous request and response unless there was some sort of like droppage or policy stopping the response. So for every request, you might see a 400 or a 200, depending on what you're looking for. Remember that it's always starting at the client side, then to the server side, never the reverse. There's different timeouts and application logic that is required, and that creates an opportunity for malicious behavior. One such malicious behavior is called the slow loris attack. Not Solaris, but slow loris, just like the actual slow animal. You want to find a balance between the TCP and application timeout logic for connections that are not complete. This attack is focused on layer 7, which defeats a lot of denial of service security contexts and appliances that are not application aware. Here we see that HTTP allows the slow loris attack by allowing high amount of timeout, saying, hey, I can't send everything right now because of my slow connection, but I can see uncompleted, H, followed by the TTP, GET request, it can actually slow down everything by making a single connection, right? A single stateless connection at the HTTP level and never sending the final TA or request in a timely manner before it times out. If you set your timeout too long for the web server side, and someone does this repeatedly across multiple hosts, you could fill up and crash your own web services, but not actually cause a network easily findable attack from a layer 3 and layer 4 perspective. In addition to IPSs, you also have the idea that you can evade them. So we have evasion attacks. So over here, remember when we talked about fragmentation and how things can overlap. If you have an overlapping fragment, the IDS can see perhaps the C or the actual data stream that is overwritten right here. But the in-host can see your IDS or IPS can only see this based on how it handles fragmentation overlap, such as dropping something. So you may reject or drop the inspection because it's invalid to begin with, and it hopes that the in-host stack, the in-TCP/IP stack, on the in-victim side will not see the actual A, right? Then you're actually seeing the C because you have a fragmentation overlap of A to C or C to A, depending on what you're looking for. That's an example of evasion of IPS controls, when you want to reject a packet based on how the IPS may reject it based on it thinks it needs to drop because outside of specifications for fragmentation overlap. And so it might let the items pass through and never alert you on it, if depending on your mode of your IPS or IDS, if you're inline blocking or if you're just doing simple alerting. You also have insertion attacks. So insertion attacks means you send more data that the IDS or IPS is supposed to see, and the signatures produce a false negative because now you're inserting additional information in here. Instead of attack being detected based on the signature, it's attack with an X inside, and therefore, without verbose signatures, it can actually have an impact on the detection of capabilities. So you're inserting additional loads such as bad checksums, time to live values inside a packet for a specific payload. Remember that payload doesn't need to be sent in one data segment. It can be sent across multiple items such as fragmentation or smaller packets as a whole as part of your total payload within the TCP connection timeout period. So IDS versus IPS, intrusion detection system as opposed to intrusion prevention system. The IDS sits on usually a tap or a switch that port mirrors everything, and it just stays passively out of band. So in case it goes down, it doesn't affect your actual network performance. Intrusion prevention systems stay in line at all times, where it actually has to actively block or deny traffic using decisions. Now, to scale, north to south makes a lot more sense with the inbound, and then east to west, your IPS can actually find traffic between different ports and different hosts at the network layer as well. How do we do so with passive or IDS port mirroring? Well, you connect to a switch, and then ports A for host A and ports B is mirrored to a port C. And there's a problem with that, and think about this for a second. Pause the video and think about it. Okay, did you think about it? So if I have traffic going in between ports A and B, and I have a single port, each of these is 1 gigabyte per second. 1 gig ports. What happens if I'm saturating both? So each of these are operating at 100% 1 gigabyte per second. If I combine those and try to filter them into a 1 gigabit per second single port, what do you think is going to happen? It's going to drop all that traffic, or it might crash the switch themselves. So the switch actually takes a performance hit, and you might overload another 1 gigabit per second port. So the port mirror that you do monitor must be something like a 10 gig on a 10 gig switch or a 10 port switch. So you have to keep in mind the total capabilities of your total port mirroring analysis. In Cisco, we call it span port, which is switch port analyzer. An alternative is to put a tap in line. These are layer 1 devices that fails open if you're using copper. If you're using fiber optics, that's not capable of failing open because you have to have light and electricity to start with. With network taps, you insert them between one switch and another or one switch and a router, and it creates traffic port mirroring without actually utilizing resources on the switch. They usually are sized bigger, so you have your monitoring interfaces at a larger scale, like 10 gig. versus multiple 1 gig network interfaces right here. That's all there really is to it. And we're talking about protocol termination themselves as well. You have to be in line to decrypt traffic. And so what does that remind you of? Termination, creating a new connection on either side. Starts with a P, proxies. So if you actually want to inspect and decrypt traffic for your IDS, data loss prevention, antivirus, you must make sure you do termination. Now, there is an issue with that. There's privacy implications, especially in the EU. Understanding the laws and what your compliance and security requirements are is really essential to determining if you should enable decryption and termination or not. You can allow decrypted port mirroring instead, stay out of ban instead of passing it for inspection logic. But if you already have something in ban, you might as well have another IPS inline right here to see the decrypted traffic and go ahead and drop that traffic accordingly. You can do so with SSL, TLS, and SSH. These are common protocols for termination. UTMs usually do that for you, but they may not provide you the raw port mirroring decrypted traffic. That could be just built-in mirroring traffic inside its own software blades. Okay, let's take a quick break, and then when we come back, we'll continue our lecture plan on proxies and port payloads. All right, welcome back. Hope you had a great break. Let's continue our discussion related to IPSs and how they deal with proxies and how do we do an inspection of payloads as a whole. Two IDS or IPS engines that are commonly out there, and that's free and open source. It's Snort and Suricata. The IDS engines pretty much are forks of each other. Suricata is actually a fork of Snort, and Snort is actually a fork of TCP dump, which is a very old school tool that operates at layer 4, allows you to do packet capturing and other filtration. Ultimately, you have an engine that does the following. It takes inbound traffic and decodes it into the proper format. It decodes it from actual wire information into a readable packet capture format, which we call libpcap. The preprocessor actually takes this and actually preprocesses things to normalize HTTP, understand base64 encoding when it sees it, and many other things such as RFC 793 TCP, understanding what is anomalous and not. Once it preprocesses that data, it goes to the detection engine, which has rules. And then, of course, you have your actions and alerting based on that. Both engines are commercially available when integrated with different products, or by themselves, they're allowed to be downloaded, and you can have open source rules at any point. Because they're both backwards compatible and forks of each other, they actually utilize the same rule sets at the base layer. There are different differences based on each engine requirements and what they do support. But here's a basic Snort rule header syntax. I have an action, which is alert, could be drop or reject or pass. The protocol that I support, source and destination based on variables or a list such as 192.168/24. I'm going to put that as a list instead if I want to. The direction and the destination port as well. Pretty straightforward. Until we get to what else we need to check, because do you see anything related to payload here? No, this actually looks like a layer 4 tuple, but let's get into our actual rule-based syntax. So I populate the header so far. It looks just like an actual stateful firewall rule. Tuples of source and destination IPs and ports in a certain direction and what we want it to do, except for the actual establishment of TCP, right? Because this doesn't necessarily need to be TCP, it could be UDP, ICMP, whatever. Now, what gets interesting is the Snort rule composition. So we actually have a rule body in the message here. We say my alert message looks like this, and we're going to say look for the word root, case insensitive. So how does that body translate? Well, we have our message and our argument here with our option. Notice that we have our parentheses here and ending with a semicolon for every rule option. Let's take a look at content. Content is the data that finds either in terms of hexadecimal values right here, which you actually utilize the absolute signs, or content in terms of a string. And remember that all of these are case sensitive until you actually use a no case clause. And this is looking for whatever's in the pattern of the data payload, not up here in the header information. Right? That's already taken care of up here. This is always in the data payload after all the headers are processed. Again, if you wanted to see ABCD without the case sensitivity, you have to have no case actually attached into it. Now, offset's an interesting one. As we're adding into our rule set, notice that we're saying we're looking for ABCD, but we want to say start at 2 bytes, skip 2 bytes before you actually go ahead and trigger on an alert. This is because that sometimes maybe a standard header or maybe the application has junk in the front and you don't want to be evaluating based on that. You always want to start off with an offset. That's what offset is, which means skip certain amounts of bytes before looking at the payload, triggering on the payload. Our depth is a different story. So how far? So I can use offset, which is skip 2 bytes, but I also say in depth, here's my maximum upper boundary. Only go in the first 4 bytes of a payload. So if I have offset, which is skip 2, let's say I have 4 bytes total. Well, let's say I have 6 bytes total. 1, 2, 3, 4, 5, 6. I'll skip 2, so I'll start my connection evaluation here. But with a depth of 4, 1, 2, 3, 4, I don't evaluate these 2 bytes anymore. I can only evaluate these 2 bytes, which could be, unfortunately, the first A and B instead. Then there's the distance option. How far into the payload should Snort ignore before starting to search for the specified relative pattern, right? Distance is all about relative of the end of the previous pattern. So if I have 2 contents, ABC and DEF, make sure there's at least 1 byte of space between DEF for it from the previous ABC match. Next, we have the within option. And make sure that at most, the X amount of bytes are within between pattern matches. So instead of saying skip or something of that nature, right, we would go ahead and say, hey, ABC and EFG must be within 10 bytes of each other instead. Here's a summary of what detects and what isn't detected. So the green is what is going to alert and detect based on the depth. So if I have payload and I have a certain amount of depth here, I start triggering based on that depth of the skipping. So my total depth to me, I'm going to trigger all the way up to here as my max. My offset, unfortunately, says skip all this payload right here and start here instead, I guess. Also, I can say distance. So when you matched here, how long before you need to match here? Or how long before you need to skip before you match here? And of course, you have within the first match here, am I within X amount of bytes, 10 bytes, to be able to alert again? So those are all how you use them together relative to understanding what you need to find within a payload. You don't need to utilize all of them together, but you can utilize them in combination to make yourself a robust and very healthy payload inspection. One thing before we want to move off our options is to go to negate. But I want to say not, right? Not EFG ever. You can add it in there, but you always want to add it at the end as opposed to the beginning. Negates are basically saying I have a very low performance and not knowing what I do need to look for, but I just know it's not going to be that. So I may want to make sure that within ABC, within 10 bytes of not matching up EFG. So within 10 bytes, I can say ABC, but DEF would match as long as it's in 10 bytes in between. Or XYZ, because nothing is EFG. And so the problem is if you use negate too often, you're going to have lower levels of performance because there's more rule matching logic that has to go with it. Now, not specifically with a true rule option, which we call content modifiers, we have something called buffers. So if your content is part of a very particular protocol, such as a header, such as HTTP URI, you can match based on a very specific payload as opposed to generic all payload after the actual header processing, which is up here at layer 4. Now we can process anything at layer 7 at HTTP using this buffer. Here's an example of multiple buffers based on the HTTP preprocessing. HTTP method right here, the headers themselves, the cookie, and of course the body, which is after all of this processing. You can analyze and reference any kind of content in combination with these different buffers to get your rule more pinpointed and higher performant. There's also the idea of fast pattern options. So you want to match on the content that is the most long. So instead of saying, if I had content of ABC, but I also had content of A, B, C, D, E, F, fast pattern basically says match this first and stop processing the rest of the rule. This saves resources and whatnot. So you actually have, once your fast patterns at the very start, with the longest rule match whenever possible, so that you have your rule evaluation ready to go. And if you want to match specifically on a string, fast pattern matching will give you higher performance inside your IDS or IPS engine. Another option includes the Perl regular expression. Regular expressions are kind of interesting because you can actually say, hey, I don't want to just match on A, B, C, D with no case, but I also want to match A, B, or C, and then D. So what would this match on? Because we have a lowercase I for no case. A, B, D, or A, B, C, or even those are the 4 combinations I would match on, as long as it met the requirements of this header as well. Regular expressions are really interesting, and so the more you master them, the better you can become a row writer or even log parsing when you're actually analyzing your payload. Now let's take another break and get to a demo about regular expressions, as well as understanding how we can inspect traffic at the termination level locally on our machines. Hi, and welcome back. I hope you had a great break. Let's look into further at how we can actually inspect traffic when we have no forms of decryption going on. When I go to gmail.com, notice I have a padlock right here. This says my connection is secure and that no one on the network can sniff my traffic intentionally. If I go into my local connection, because SSL operates on TCP port 443, I'll monitor for that accordingly. If I go to test something at foobar.com, notice here that we have information and traffic going here, but I can't search for it. TCP contains, and there's nothing here. Naturally, that's because everything is connected over SSL, such as right here. Because this is a whole bunch of junk, I can't do anything about this. Now we need to utilize a proxy for this. To actually see what I did a GET request and post, and it said I couldn't find an account. To do further troubleshooting, let's look at utilizing a utility called burp. I've already installed it, and I'm going to go ahead and run it, bring it to my next screen. Start with default settings. And here, the newest burp is quite nice. It actually includes a proxy in here. I'm going to turn intercept off, which actually doesn't mean what you might think it means. It actually just means that it's going to act as a proxy, but it's not going to go ahead and pause at every time saying, do you want to allow or deny? I can intercept requests and change my settings in my replace match and actually pass through the not inspect any traffic, encrypt it wherever I need. Let's open my browser. And it's going to open a very specific embedded browser, very specific, and explicitly defined to listen, to look at my local listener. If I go to settings, proxy, it's going to use automatic proxy settings accordingly. The interesting thing is here, it's going to go ahead and do it based on a listener. Of course, you can actually change your listener from 8080 to something else. If I go to gmail.com, I can actually see some of the additional information. If I go to foobar@foobar.com, it's going to say it's not secure because something is in the middle here. But we weren't able to see that last time to begin with anyways. Let's look for a post because I'm posting information. Here's my methods. Accounts.google.com makes sense to me. Let's dig down about where I can find foobar. Here we are. Foobar.com is right here. You can also try to decode all of this by passing this into the decoder by right-clicking and sending it to the decoder. Decode the module, and it can give me more additional information if desired. Notice I don't have as much information here to go and parse out through. Back to my request and responses here. You can see all the domains. Change my scope to only include Gmail domains. And see what have I had. I had 302 moved permanently, which redirected me to www.google.com/gmail. Notice that I had to use a proxy to actually decrypt everything because of SSL decryption and termination. Let's look at some IPS-based items. I'm going to go to packettotal.com. And in the labs, you will also have a chance to download malicious packets and inspect them accordingly. I can search for a particular well-known vulnerability like a MS0867 and any kind of exploitation that has come from it. I'll choose a sample right here. And notice that I have IPS and IDS alert signature information. There's a timestamp in the alert and the tuple information about the flows. Let's look at the graphs and timelines associated with this malicious traffic. Here's some statistical details about how I can actually log and understand parsing information and destination select port. Really useful stuff that you can still grab out of any PCAP whatsoever. Here's a timeline of interesting events. But more importantly, let's look at the IPS signature that created suspicious activity. It has some message information here. So let's go out to malicious, known malicious activity. And we're saying we found ghost and ghost Trojan detection, spyware. Let's use this one. I'm going to search for this signature. We're going to go into this signature right here, and then we're going to search for what this looks like. So what we have here is a snort-based signature. We have our standard header information here, along with the information. So we have a size in between 100 and 300 bytes. The content includes ghosts within a 5-byte payload. And it has some reference information. So a very low entropy based tagline that this is ghost infected traffic of malware related to that. So, but what if I had PCRE rules that have expressions, PCRE emerging threat rules that weren't so simple, that need to have variations of ghost? Well, I could do this. I could go to regex 101 and let's look for variations of ghost accordingly. Original capture basically said they wrote it like this. Well, what if someone wrote it like this? Or like this? or like this. Well, then we have a problem because we're just slowly changing each of these signatures. Let's look at our metadata right here, and you can also follow along using a regular expression cheat sheet. Take a look at all of these, and you actually utilize one or more of these cheat sheets together in combination. So, if we want to look for variations of ghost, this will be case sensitive. We can also say /I here, but that's not going to help us. What we really want to do is look at what we have over here. We want to capture a character case range. So we might want to have the idea of, well, we're definitely going to have something here. So we'll have case sensitivity, upper and lower using POSIX if we desire, and other information. I'm going to say case insensitive accordingly. So let's do that. Capture group here. And then we want that to be now we're saying our first capture group is literally case insensitive when we look at this. So we look at and we also say this as a startup string. And then let's make sure we have our exact case insensitive matching. So we have pattern identifiers here. And just to be sure, we know what we're doing here in terms of insensitive. Here's how you would use it. A /I behind this. Okay. So we're going to say A or A behind. But I'd rather do something like this. What if I knew I was going to have always a GH in front of it? So I would rather have, I can do a range of G or G and H or H. And I might have a digit, or I might have a O. Here we go. And I'll put this as a content match. And then I'll always have some form of ST. Perfect. Now we're matching on all variations. And we can make this a capture group. And so it will always match on that capture group all of the above on all variations of ghost based on what we just did. If I wanted to match on variations appropriately, I can also say this. Now, we create multiple capture groups. And now we've captured all variations with ghost using this regular expression pattern as opposed to relying completely on a static pattern that makes sense for here. So if someone ever changed the pattern to match, we don't have to rely on this static signature. We can actually modify the signature and include regular expressions to do so. Let's try one more example. 10, 10, 10, 10. Here's some sample structured IPv4 addresses. Well, knowing what we have in our captures, let's look at our cheat sheet if we can again. Now, while I could say, hey, /d or any one or more, what's the problem with this? Is this a proper IP address? No, of course not. So there's a problem with that. We need to shore it up. So D plus means one or more digits. Well, how can we actually limit this? Because we know that at least there is a minimum of 1, but there's a maximum of 3 digits. I'll say 1 to 3 instead, using a quantifier. Now, as you go through, I'm not expecting you to be a regular expression master, but play with it, especially in your labs when we get to it. Now we have an ability to say, hey, that's not a valid IP address. And in fact, we see this dot here, we actually need to escape it. So that we always match on a literal, so it's not matching on 1 or more. Now, much better. However, is that a valid IP address? The answer is no, because the maximum you'll ever have is 255 across. And really, that really means broadcast address. So while that's not perfect, it's still more tightened up, and it's not overly complex. So that's it for our demonstration today. Hope you enjoyed it. We'll see you in the next lecture.